Introduction to waves. To this point in the course, we have discussed energy being provided to an object as a result of work being done on it. We can do work on electrons to move them to where they do not want to be, causing them to hold onto electrical potential energy that can be harnessed later. We can do work by pumping water up to a storage tank where it can then be released, allowing us to collect its gravitational potential energy as it falls. We can also burn fuels, chemical energy to power out applicants, cars, etc. Energy in the universe can also be transferred via waves. In physics, wave is transfer of energy as a result of an oscillation or vibration. Generally, these vibrations act like dominoes, causing nearby particles to also move and cause a cascade of movement, which transfers energy overall before the particles return to their previous positions. This is worth emphasizing because vibrations cause things to return to prior position. Waves only transfer energy, not mass. Every wave can be broken up into several parts, labeled with letters A, B, and C. In the space below the diagram, identify the name of the part of the wave that's labeled. A is amplitude, maximum displacement of wave from rest position. In sound, more amplitude means the louder it is. In light, more amplitude means the brighter it is. B. Wavelength. It is measure of length of wave cycle, most easily measured as distance between consecutive crests. C. Trough. Lowest displacement of wave known as valley. D. Crest. Highest displacement of wave known as peak. There are also a few other terms that you should know about wave properties. Wave pulse, single oscillation. Frequency, number of wave cycle per second measured in hertz. Period, duration of wave cycle in seconds. Phase, starting position of wave. Types of waves. Although all waves, whether they're sound waves, light waves, water waves, etc., transfer energy through vibration, there are different ways in which this energy is transferred in terms of direction of the vibration. Firstly, waves can be divided into two categories, transverse and longitudinal waves. There are two diagrams at this side with an example of each, where the waves are moving to the right. Describe the motion of the wave compared to the oscillations in the space provided. Transverse wave. Oscillations are perpendicular to wave motion. Light is an example. Longitudinal wave. Oscillations are parallel to wave motion. Sound is an example. Waves can also be described as mechanical, meaning that the only way that particular wave can transfer energy is if there is some kind of material or particles for the energy to travel through. We often call this material the medium that the wave travels through. An example of a mechanical wave is a sound wave. Sound waves are longitudinal waves that involve the compression and expansion of air or other substances to transfer. There is no medium for the sound wave to travel through. Interestingly, light is a transverse wave that is not mechanical. Light can travel through the emptiness of space and therefore doesn't need any particles to vibrate to propagate its energy. As we will learn later, the oscillations for light are of electric and magnetic fields. Here are some questions that might pop up on Regents. Number 1. The frequency of a sound wave determines its pitch. 2. An electric guitar is generating a sound wave of constant frequency. Increasing which of the following characteristics would result in increased loudness? Amplitude. 3. Waves transfer energy between 2 points with no transfer of mass. 4. The time required to produce one wave cycle is the period. 5. A common characteristic of sound and light waves is that they both transfer energy. 6. The distance between two crests in a wave is the wavelength. 7. If the period of a wave decreases, its frequency increases.